Hello, good morning. So today's lecture should be a short one. We will talk about the strongly connected components. And then, yeah, so let's wait for 1 more minute. Okay, so let's start. Okay, so today we will talk about or we will define a concept called strongly connected components of a directed graph. And then the focus of today is to give an efficient method to find all the strongly connected components inside the directed graph. Okay, and then so see, let us say G is a certain some directed graph. We let U and V to be two vertices in G. And then first of all, we will talk about the concept of mutually reachable. So from the meaning of the word directly, it means that when two vertices U and V are mutually reachable, it means that we can reach U from V and reach V from U using a directed path. So there is a way that we can travel starting from U, follow a directed path to V, and also we can start from V and follow some directed path back to U. So in such a case, U and V, we call them mutually reachable. So if this is the case, then we will write this as a shorthand notation. U with a like double-sided arrow, V, it means that U can reach V and V can reach U. Okay, and here we assume that although there may be no edge joining U to itself, but then here we will just simply assume that U is reachable to U. Okay, and then if you still recall something in that you have learned in discrete mathematics, we have talked about relation. So this is a certain kind of a relation between two vertices, right? Given a certain relation, we may have some extra property of this relation. So if it satisfies certain property, then the relation will be having some other extra property. So we claim that this mutually reachable relation is a relation that satisfies the three properties called reflexive, symmetric, and transitive. So this is something that we have studied in discrete math, these concepts. Reflexive means that if any vertex U is related to itself by this relation, so if U is always reachable to U, then it satisfies the reflexive property. And this is the case for us. So if U is mutually reachable to U, that means that, yeah, it is true. Okay, so in that case, it is reflexive. Now, symmetric is another type of property. So symmetric means that whenever U is mutually reachable to V, is it true that V is always mutually reachable to U? Now we see that this definition of mutually reachable is symmetric. So in that case, yeah, this is a symmetric relation. Okay. And finally, we will see this is also true. Now, if someone tells you that U is mutually reachable to V, and also V is mutually reachable to W, then in such a case, given these two conditions, we will always tell that U is mutually reachable to W, right? So if this is okay, then we see that it is a transitive relation. In discrete mathematics, we see that whenever a relation is reflexive, symmetric, and transitive at the same time, it is an equivalence relation. Equivalence relation means that we consider these vertices are equal to each other, just like the equal sign that we have. Okay, so here equal means that we can classify the vertices of the graph whether they are equal or not. But the equal here means that whether they are mutually reachable or not. So in that case, so let's see this as an example. Using the mutually reachable relationship, we can actually partition or classify the vertices of the graph into groups. Okay, so for instance, let's say this red part. Okay, so for this red part, we will see that R is mutually reachable to S. Reason, R can reach S by way of using directed path, and S can also reach R using a directed path, right? So R and S are mutually reachable, S and W are mutually reachable, R and W are mutually reachable, and so on and so forth. But on the other hand, we see that R and T, they are not mutually reachable. Of course, we can see that R can reach T, but there is no way that T can go back to R. So in that case, R and T are not mutually reachable. Now here, we are classifying the vertices if they are mutually reachable to each other. And we will see that, okay, in that case, we can have this red group of vertices, and then we have this green group of vertices, and then we have this purple group of vertices. Within the same group, all the vertices, you can think of them as equal in the sense that they are mutually reachable to each other. So this is the given directed graph, and given a directed graph, we can use the mutually reachable relationship to partition the vertices into groups, and then each group here is called a strongly connected component because this is like a component of the graph, and then it is strongly connected in the sense that every node can reach any other node. Okay, so let's see some property of the strongly connected component. So suppose that G is a directed graph, and we let G transpose. Okay, so we have actually defined G transpose before. So what is G transpose? G transpose is the graph obtained by reversing the direction of every edge. So remember why we call this a transpose. So recall that for any graph, we can represent it using the matrix representation. So if we perform the transpose of the matrix, then what does that mean? It means that originally, if there is an edge from U to V, now there will be an edge from V to U instead. So it is like reversing the direction of every edge. Okay, and then there is an interesting property. We can see that G and G transpose, they will have the same set of strongly connected components. To prove this, we just can, so this is easy to see. Yeah, to prove this, we will see that if U is mutually reachable to V in the graph G, it happens if and only if U is mutually reachable to G in the transpose of the graph G. Yeah, because UV is related in G implies that UV is related in G transpose. The strongly connected component defined by G will be the same as the strongly connected component defined by G transpose. Is that okay? Okay. Now, so we are not going to prove this. This theorem is left as an exercise for you. And now let's take a look. Okay, now we are going to talk about the component graph of G. So what is a component graph of G? So first of all, we find out what are the strongly connected components in this graph. This is the original graph G. And next, we will use a single vertex to represent the whole component. So here, this is a red component, right? It has three vertices. We will use a single vertex, let's call it V2, this one, to represent it. For this green one, we will use a green vertex to represent it. This is a purple one, we use a purple one to represent it. And then the edges are still there. So there is an edge from this purple to red. So there is an edge from purple to red. There are two edges from red to green, but then we can simply represent it as an edge from red to green. We can use two edges. That's also okay. Yeah. But in any sense, we can always make the graph simple so that we will remove all the self loops. Yeah, you don't see any self loop actually. And then we will also represent each multiple edges to a single edge. So it is called a component graph here of the original graph G. Is that okay? So here it is like we are contracting each of the strongly connected component into a single vertex, and we get this component graph. So there is a theorem. We will see that this strongly connected component graph, this component graph, we do not have any directed cycles. So it is acyclic. So there is no cycle here. Because if there is a cycle here, then what does that mean? Let's say there is also an edge joining V3 to V1. That means that any vertex in V1 can reach any vertex in V3 through this edge, and then they are strongly connected and can reach here. And on the other hand, because there is a back edge here, so every vertex here can also reach V1, any vertex in V1. So in that case, the vertices in V1 and the vertices in V3, they should belong to the same strongly connected component. So there is a contradiction. So in such a case, the component graph has to be acyclic. Okay. And now, so this one, yeah, so the proof is here. So it's rather simple. And now, so today's purpose is I have a graph G. I want to find out which vertices are in the same component. So here we are going to apply the DFS algorithm to help us. So let us see what happens if we perform the DFS on the original graph G. Okay, so we are asking this question. Suppose that U is some vertex that has the largest finishing time when we perform DFS on G. So which component can U be located? Can U be here? Can you 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 be here? So let's find out. Let us use this as an example. Okay. So suppose that we have a certain vertex that is having the largest finishing time when we perform the DFS on this graph G. Now, can this be this vertex? Is it possible that this is a vertex that has the largest finishing time? Now we claim that it is no. Okay, the reason is that, okay, there are two cases. So first of all, we see that there is a green component here, right? This is a red component here, and red points to green. Okay, so here, let's say there is a vertex with the largest finishing time here. Then we ask, how about this vertex? Okay, will this vertex, what will happen for this vertex? Okay, so first of all, among these two vertices, one must be discovered first. If this one is discovered first, then what does that mean? Okay, oh, I should say, among the components in red vertex and the component in green parts, either we have some vertex here to be discovered first, or we have some vertex here to be discovered first. Okay, now if the first one to be discovered appears in this red component, that means that by the time, let's say this is the vertex here, by the time that it is discovered, all these vertices are white. So in that case, this vertex, by using the DFS, will reach every vertex here during the DFS search of this vertex. So in such a case, the finishing time of this vertex must be larger than any of the vertices here, implying that any vertex here cannot have the largest finishing time. So this is the first case. If the first vertex that we are discovered appears in red rather than in green, then the red one will have a larger finishing time. On the other hand, if among the red and green components, the first vertex to be discovered lies in this green part, then what does that mean? So, but let's say this is the vertex, whatever. Okay. So in that case, we will see that by the time that it is discovered, all these parts are white, and then they are connected to each other, right? Strongly connected. So in that case, the DFS of this vertex will be visiting all the vertices in this whole green component. And by that time, none of the vertex in the red part will be discovered because it is not reachable. So in that case, all these vertices will finish the DFS part before we can start anything on the red part. And in that case, the red part vertices must finish later than the green part. So in such a case, we also can see that none of the vertices in the green part can have a larger finishing time than a vertex in the red part. Okay, conclusion. So this is what I want to say. This is the key observation. If a vertex appears in the component that is pointed by another component, then this vertex cannot have the largest finishing time. So if U is a vertex with the largest finishing time, it cannot appear in V3. It cannot appear in V2 because V2, there are arrows pointing into it. Cannot appear in V4, cannot appear in V5, but it may appear in V6, it may appear in V1. Is that okay? So as long as it is pointed by an arrow, then the largest finishing time node cannot appear in that component. Okay, so this is the key point. And this key point allows us to, so this is what I'm summarizing it. Okay. The node finishing last cannot be a vertex of a SCC corresponding to V, where V is a vertex with at least one incoming edge. Okay. Okay, now, so this is the proof. We just mentioned it. So, okay, now, this is an interesting thing that helps us to locate the node with the largest finishing time. So it may be in V, it may be in V6. And what we want to do next is we want to find out all the vertices in the same component as this vertex. So how can we do so? Oh, this is a very clever idea. What we are going to do here is we are going to make GT. We are going to reverse all the edges. So I'm showing the reverse of all these edges that you see in the component graph. But then you will also you will also notice that we are also reversing the edges inside each of the components. And now, what will happen? Okay, if we now start running DFS on U in the reverse graph, so we are going to run. So if U is in V6, then running DFS on U will visit exactly all the nodes in this golden yellow part, right? On the other hand, we see that the last vertex U could appear in this V1, right? So if we are now starting DFS of U in this reverse graph, then what will happen? U must be visiting all the vertices in this purple part, because of the white path theorem. So we will visit all the vertices in this purple part, but then we cannot escape from this purple part because the arrow are in the opposite direction. So we can only visit nodes that is in this component. So what does that mean? So if we start the DFS on the largest finishing time node, we will be visiting all the nodes in the corresponding component of U. And after that, we can, so let's say U appears in V1. So after that, what will happen here is that we can find out all the nodes here. And then all the remaining nodes are still unvisited. And we can continue the same process. We want to find out among all the nodes that are still unfinished, undiscovered, which one has the largest finishing time. The one that has the largest finishing time could be inside V6 or inside V4 now. Because for all the other components, they have arrows pointing into it. And then we continue to apply the same process. We perform the DFS on the currently undiscovered node on the reverse graph, and then we can, let's say we may be able to find out, okay, let's say the next node appears in V6, so we are going to perform the next node's DFS and then discover all the nodes in this golden component without touching any other part. So in that case, we will see that by running the DFS based on the largest finishing time, we will be able to extract nodes in one component, and then the next component, and then the next component, and so on and so forth, one by one. Okay, so this is the summary of the algorithm. So how can we find out all the strongly connected components of a certain graph? What we can do here is we perform the DFS on G from the beginning, and then we construct the transpose of G, and then we perform the DFS on this transpose graph. So while some node in the transpose is still undiscovered, we let U to be one of them. We perform DFS on U. After that, we extract the first component that is containing U. And what we want to do next is we check the next undiscovered node if it is still there, and then find out one which has the largest finishing time, and then perform DFS on it. We perform this again and again. Let's say we perform this while loop k rounds. That means that we have exactly k strongly connected component in the graph. Okay, so finally, so the correctness of this one, yeah, you can see that yeah, you can try to think about this by yourself. Yeah, it can be proven. The correctness can be shown by using induction. But let us analyze the running time as well. So how much time does it take to perform DFS on G? So it will be linear time, V plus E, right? Now how about the construction of the transpose of G? Although we mentioned that, we mentioned that the transpose is related to the transpose of the adjacency matrix, but we are not going to use adjacency matrix as our representation. We are using adjacency list. So the transpose can be easily obtained by looking at each edge in the graph G. Let's say there's an edge UV. We will add an edge VU in the graph GT. So in such a case, visiting each edge of G, we'll get an edge of GT, and then we will construct the adjacency list of GT based on reading all the edges of G. So in such a case, we can construct the adjacency list representation of GT also in linear time. And finally, the third part here, it seems like we need to find out the latest node with finishing time, but it's not necessary to do so by doing the searching of the node. Yeah, we can search. Okay, so what we are going to do here is we can maintain a list of nodes after the performing of DFS on G. We can maintain a list of nodes ordered according to the finishing time in decreasing order. Okay. And now we can also maintain a list of whether a node is discovered during the DFS of GT. So we will first get a node according to the largest finishing time, and then run DFS on it, and then update the nodes that is being discovered. And after that, we will try to extract the next node here according to the latest finishing time, and then we check whether the node is discovered or not. If it is not, then we run DFS. If it is discovered already, then we will move on to the next node, and then until we find one which has not been discovered, and then run DFS on it. So in such a case, we do not need to do searching. The searching is done by maintaining the list of nodes with finishing time here. So this can be extracted in amortized constant time. So in the end, this while loop is just simply the DFS on the graph GT. So it also runs in V plus E time. Okay, so yeah, that's all for today. Yeah, actually, so before I stop here, I want you to actually compare this algorithm with the topological sort. Now in topological sort, we have a deck as an input, right? And then by running DFS once on it, then we can get linear order. And similarly here, the similar part here is we are getting a certain, we are getting a certain undirected we are getting a certain deck here at the beginning, and then this is the process that we are doing using the DFS search. But then when topological sort, you don't need to care about whether there are some nodes that are strongly connected so that it can confuse you about the relative ordering of the nodes. Here, we need to do a second DFS so that, and also on the reverse graph, so that we can extract this component one by one. So the two algorithms are really similar. Indeed, we can use SCC algorithm to solve the topological sort, because for topological sort, we are seeing that each vertex by itself is a strongly connected component. So we can actually do so, but then we don't do that. Okay, so I think, yeah, it's nice to compare the two and then find the similarity. Okay, so let me see if you have any question. Yeah, if not, yeah, that will be the end for today's class, and then I will prepare the assignment for you as an exercise to check your understanding. So all the concepts like BFS, DFS, topological sort, and strongly connected component, they are related to graph searching, and then, yeah, and so we will group them as one batch of exercise. Okay, yeah, that's all for today. Thanks for coming, and then see you next week.